Let's do a cantilever problem. This is another type of problem that's a torque problem, and so it's pretty typical. A cantilever problem is something similar to a shelf that's inset into the wall. Okay, this is called a cantilever. So bridges are made this way. Sometimes houses are built this way into cliff sides and things like that. So this is a particular design. So let's try this problem. It says when a 42 centimeter long wooden shelf of mass 3.4 kilograms is fastened inside a 1.5 centimeter deep slot in a vertical support as shown in the figure, the support exerts a torque on the shelf. Exert the magnitudes of the three vertical forces acting on the shelf. So what are these forces? Well, we've got the force of gravity acting on the center of gravity. And then you have, you've got the force here on the shelf acting upward, right? So there's this point here that's exerting the force up. So we'll call that the force up. You can call it whatever you want. It's a normal force. And then there's this pressure down on this end. So this is your force down. These are the four forces. Now you can kind of, let me see if I have, you can take a ruler and kind of simulate this, right? You need to, right, if you want to balance this, right, you can by holding the ruler like this, right? This represents that corner of the shelf, and this represents the inset, the far end of the shelf. And the heavier this is, the shelf is, the more these two are going to have to balance. So, you know, if this force is too big, it's going to go up. If this force is too big, it's going to go down. And the pivot is this force here. This corner of the shelf is the force. It's going to always be what you're pivoting around. So that's what that's where we're going to make our fulcrum, right there. Okay? So now when we set this up, we have net torque clockwise equals, notice we always do the problems the same way. The hardest part is the setup. So it's very important that you clearly draw and take your time to figure out where the fulcrum is and what the forces are so that you can really visualize what's happening. These are not difficult to solve once you have an understanding of the situation itself. So take your time with the setup. So what information do we have? So we know that the whole thing from end to end is 42 centimeters long. And this part here, right here, is 1.5 centimeters deep. And we know that this is 3.4 times 9.8. So that gives us a weight of 33.3 newtons. So that's our given information, and our job is to find all three vertical forces. We've already found one. Now, which forces are clockwise and which are counterclockwise? If this is the pivot, then this one is pulling clockwise, and this force is pulling counterclockwise. So the clockwise force is the force from the center of gravity times its radius, and you can see that this is acting right at perpendicular, so that's sine of 90, which is 1, so I'm not going to write it. And then the other one is the force down times the distance downward. So this is what we're looking for, the force downward. The distance from the pivot is 1.5 centimeters. Now in terms of using units, I always like to convert to meters, but you don't have to because as long as you use all the same units, the distances will just cancel regardless. But just to be in good habits, I'm going to put mine in meters. And now this is going to be 42 minus 1.5, which is 0.405 meters. So now this becomes pretty easy to solve. You end up with 433 newtons is this force downward. So now you have to solve for the upward force. So for this, I'm just going to draw a free body diagram. Just at a point. The reason why I do this is to make sure it's clear to me that I'm not dealing with torque It helps me to visualize things better. You can certainly just use this. You don't have to redraw it, but I highly recommend that you do. I find it much easier, and I assume that if I find it easier, you will too. So now you can just set up your Newton's second law, right? Because it's not accelerating, because it's in static equilibrium, and this becomes pretty easy to do. So you end up with the force up is 466.3 newtons. That's a typical cantilever. I want you to imagine, though, that of course you could put things on this shelf, or right? You could have other forces because, I could say, how much weight could it support at its end, before collapsing? And you could have another force here that would make this a more complicated problem. It would add another torque acting on this beam, but the solution is the same. The type of solution is the same.